All right, recording is rolling. Welcome to Thursday, September 28th. Ooh, I got something special for you guys today. Varignon frame. So you guys got this lab page right here. I'll walk you guys through it, what it's about. So other things going on. You guys remember your chapter 4, chapter 5 puzzles are due tomorrow. Some of you guys have already turned those in because we've covered all of them in class, all the circle ones. That's all I'm looking for, right? If you're really into this, I want some extra ones, and those are there too, but there's the circle ones I signed going over this class. You guys' Forces take-home quiz due on Monday. Projectile quizzes, I want to get back to you guys. I'm just waiting for like 5 or 6 students to turn this in, but if I don't get those by tomorrow, then I just have to put a 0 in, so double check, make sure you turn that in. And then I'll get those back to everybody on Monday as well. Okay, so this, All right, so what is this Varignon frame? What's this about? Let me just share my screen here. All right, show you guys with this video. So the premise here is going to be: suppose you're going to build a factory, and you're building or you're making some kind of product, right? Which has a different import material, right? So different input materials. So maybe you got like here on the screen here, got 3 different input materials, and I'm going to make some kind of output material. So the example I'd be using is maybe you're crafting pencils, right? So the pencils, maybe you need some source of lumber. So you're getting lumber from a forest. Maybe you need some source of like graphite for the lead. Maybe you need something for like the erasers, right? So you bring that all together to some central location, and then you're making these nicely packaged rectangle type boxes that you can ship to like a nearby city, right? Market center, right? But each of those inputs and also the final output has some kind of associated transportation cost, right? Like maybe the lumber is particularly expensive to transport because it's like this weird shape. It's really heavy. A lot of it's going to be shaved off and not used at all, but maybe you're transporting it there in the first place, right? Or something like that, right? Maybe the final output, like those pencils, because they're very nicely packaged in these rectangle boxes, they're easy to ship. So maybe they're not as expensive to transport, right? So if you want to minimize the transportation costs of each one of these materials, do you guys think you want to put the factory closer to or further away from something that's really expensive to transport? What do you guys think? Closer to, right? So for example, if the lumber was particularly expensive to transport, you probably want to put your factory nearby the forest, kind of deal, right? Now, there is a solution that's based on physics, which how do you guys do? So here's this Varignon frame table. What you do is tie a bunch of strings together, and where the strings come together, maybe have like a paper cut out of a factory. I'm just kind of going to use like the knot to represent where the factory is, right? And then have a bunch of pulleys, right? You guys have a bunch of red-looking pulleys, right? Hang those over the edge of a table. I think this table has holes in it. And then hang the string down, and on the ends of the strings, oh yeah, you guys see these lab weights right here? These lab weights? Suppose that each lab weight was proportional to the transportation cost. So maybe if like lumber is twice as expensive to transport as the graphite, for example, then maybe this could be 200 grams versus 100 grams, right? 2 newtons weight versus 1 Newton weight, right? And then what'll happen is that factory will set up in some natural equilibrium point, and that point is the place which represents the lowest transportation cost. So it'll be like the optimal place to construct that factory. Oh, here, let's see, it's a close-up of these pulleys, right? You guys got some red pulleys you know how to work with, right? Here's these weights. Let's see this thing kind of in motion, right? So, you guys saw you just changed the weight. And if you put like more weight somewhere, which will represent higher transportation costs, well, that's going to move the factory closer to that point. What if you replace that with a smaller weight? Ooh, okay, now there's like a new equilibrium setup. I guess this, right? So you and your friends today can hold on to the pulleys, just have them stationary at like some locations. Right? Oh, here you go. Here's the map for you. Right, so you've got the factory sliding across, right? Depending on some location. Right? Hang some strings, weights, right? And then yeah, there'll be natural equilibrium point for that factory. So I'm gonna have you guys measure like what are the weights? Well, that's like the number of grams for each one is stamped on there, which is like a mass, so that's proportional to the weight. Okay? And then you guys got some meter sticks back there too to measure locations. Right, so here I'll do some examples with you guys because I got 3 different scenarios set up. One of them is completely filled out, so that's just an example. One of them is like halfway filled out, and one of them is completely blank. So let's look at the one that's completely filled out, this top one right here. But what does this say to do? Right. So this one says, well, one thing it says is that the transportation costs are all equivalent. Right. So got the same number for each one. This is 100 grams right here, right? Which by the way also weighs 1 Newton, right? 100 grams. Right? Maybe you just have the exact same lab weight tied to each one. Right? Right. And then I gave you guys some coordinates. Here's the coordinate of, say, like, ooh, a forest could represent the lumber. Right? Actually, I only have 2 inputs. So let's say a forest for the lumber and like a copper mine for copper. Right? And then I've got an output, which an output location. It could be like a town. Suppose there's a nearby town you're shipping everything to, right? Right. And then the 4th location would be the factory. So 2 inputs, input locations, 1 output location, and then where do you want to put the factory? So how do those numbers play out from this example? Okay, so you guys have lab tables back there, and I'll give you guys a little bit of a hint. The lab table width is 122 centimeters wide. You can measure that yourself, but that's what it's going to come out to be. Okay. So here I've got, suppose this point right here is the origin point. Let's call this 0, 0. So you guys gotta have Cartesian coordinates going on. So here's the end of a lab table. Now, some of you guys might have the middle of a lab table, but you can just mark some point as 0, 0. Okay. And it looks like I have the forest at that location. You guys see 0, 0, like a Cartesian coordinate? So I'll go ahead and draw a little tree to represent the forest. Right, there's a forest location. Okay. You want to attach one of these pulleys right there. One of these pulleys right there. You can string a string through it. Right. So and eventually you'll hang a lab weight from it. So I'll draw that one later. Copper mine, I have the coordinate 0, 122. So 0 centimeters over, 122 centimeters up. Again, like on a large map, maybe that represents like 0 kilometers over and 122 kilometers up, but we'll do centimeters. Okay. So I'll go, let's see, about there. So bam, so right about there. Okay. So this is going to be the coordinate 0 centimeters over, 122 centimeters up. Let's do like centimeters, right? Okay. I'll throw one of these pulleys right there. Hang over there. That's going to represent the copper mine. All right, copper, like a copper mine, right? What else we got? Oh, I have a town that I'm going to eventually ship all these pencils to. Suppose I'm making pencils, right? Okay. So that's 122 centimeters over, 61 centimeters up. I mean, these are Cartesian coordinates. Right? So x-axis 122 centimeters over, which I chose because that happens to be the width of the lab table. Right. So just to remind you guys here, right? This width is 122 centimeters, right? And 61 centimeters up. Hey, that's like halfway. Right? So it's like probably bam, right about there. Okay. Here's my town. Call it the town at the coordinate 122 centimeters over, 61 centimeters up. Okay. Maybe draw a little building. How about that? Got little houses and stuff on. All right. So 2 input locations, 1 output location. Right. Now, where should the factory go? Well, that depends on the per unit transportation costs of the materials. Right? Now, here I've got them all weighted equally. Oh, so I bet the factory is just going to go like basically kind of in the middle, right? Okay. But you guys can find out empirically, and the way you do it is you tie 3 strings together. Right? My last class probably has some pretty good setups going on. Right? You'll thread those strings through these pulleys. Right? And then over the edge, hang some lab weights. So this one's straight through there like that. Hang down lab weight. Okay. So start hanging on these lab weights. Maybe put 100 grams there, 100 grams hanging right there, and 100 grams hanging right there. So, right? So it's 1 Newton weight, 1 Newton weight, 1 Newton weight, right? Like that. Right? And then the factory location will set up natural equilibrium point. Right? The little smokestack, got a factory going on, right? Like right there. Okay? And that's how you know where to build a factory to minimize the transportation costs. Okay? Last thing you do is you measure it. So you guys got some meter sticks. So you can measure, like what is the coordinate is, like how many centimeters over, how many centimeters up on your map. Okay? Maybe that represents how many kilometers over, how many kilometers up. And what I got was like 35 centimeters over, 61 centimeters up. Happens to be the equilibrium point for this particular setup where it's equal transportation costs, like equal weights all the way around. Right? Wait, so now you've oh, and that is in this box right here, 35 centimeters over, 61 centimeters up. Right. Now this one I calculated, but if you did it in real life, I bet it would land pretty close to that point. Pretty close to that point. Right? again, you guys are doing the empirical setup, so you guys are just letting the lab weights like naturally tell you where the equilibrium point's going to be. Okay, I see that. Okay. The next one here, I've got 500, 400, and 200. Those could represent the per unit transportation costs. But you could very simply say, well, I've got a 500 gram lab mass there. 400. Hey, how do you make 400 grams? Can you take two 200s? Can you do that? Two 200s, right? And then, well, you could find another 200 and put it there, right? Or you could take a couple of 100s. There's 100, 100, right? Something like that. Like time to get 100, something like that. There's a different ways to do that, right? Now, I didn't tell you the locations in any of this. So this next one, I'm letting you guys choose some locations, right? But some idea of set up a natural equilibrium point. Here, there's this. What if though, here, what if instead of 5 to 4 to 2 is the ratio of those costs, right? What if instead of 500 here, what if it was like 1,000, right? So you have like a kilogram lab mass, like 1,000. Okay? Do you guys think at some point this number could be so big that it would kind of make sense to just put the factory like right on top of the forest kind of deal, right? Because it'd be like so expensive to transport. Well, I'm not even worry about transport. Let's put the factory right there, right? Right. That will be true if that per unit cost is larger than the sum of everything else, right? Here, so for example, since you have like 3 location points going on, you guys know a property of triangles? You can draw any type triangle, right? Any type triangle, right? Maybe we've got a triangle, something kind of close to equilateral there, right? What if I had like a crazy skinny triangle? What if a triangle that looks like this? Okay. And then what if I label the sides? So maybe like A, B, and C. Now this is not Pythagorean theorem that I'm doing, right? Because these are definitely not right triangles. So Pythagorean theorem doesn't apply. Okay. But what it will do is, right, isn't it true that if you take the 2 shortest sides and add them together, A plus B, that has to be greater than the longest side C? Right? This is a property of triangles. Like if the A plus B added up to less than C, then it wouldn't even close and make a triangle, right? Right, yeah, right. There's a similar thing going on here. Guys, 400 plus 200, that's 600, right? Which is more than 500. What that means is that maybe your factory is going to line up pretty close to the forest, but it's not going to be in the forest. It's going to be somewhere kind of in the middle. Okay, right, is that? And the last one is completely open, so choose like different ways, different locations. Okay, right. When you guys do that, pick one of those and try this on the back. So on the back, here the principle here has to do with. Yeah, I think I got. Here. You guys remember this poster here, right? Where if something's in equilibrium, the horizontal components have to balance out and the vertical components have to balance out, right? And if it's asymmetrical, which might be a little bit closer to what you guys are doing today, it's the exact same principle, right? These 2 sideways components cancel out, and these 2 upwards balance out with this one downward, right? Zeros out. Right? Well, you can test this empirically. So I want you guys to see if that actually works. You're going to have 2 resource locations and 1 town, right? So you got 3 locations. Your factory is like right in the middle. Suppose you center a Cartesian system on the factory and you zero out one of the one of the strings. Okay, that's what it says up here. It says like zero out one string. So you have a Cartesian system that's aligned with one of the strings, right? Right. Then you guys got some protractors back there. Protractors on those lab tables. Could you guys measure what is this alpha in degrees and what is this beta in degrees? Right. And from that, you can get components. So you can figure out, well, how much is this guy pulling, say, like to the northeast? Like how much north and how much east? Oh, let's just sine and cosine components from this alpha. And this guy pulling northwest. How much north? A little bit. How much west? A lot. Okay. Well, let's just sine and cosine components from the beta. Right? And whatever lab weight's hanging over, suppose you have this guy. This guy weighs 5 newtons, right? 5 newtons it weighs, right? So down here it says, well, what are those 3 weights that are hanging? Maybe you have like 5 newtons and 4 newtons and 2 newtons, for example, something like that. Right? Measure what is alpha, what is beta. So we figure out like 20 degrees and right 15 degrees. I don't know, how many degrees. Okay. Then you can calculate with sine and cosine. What are these components? That's what these are here. These are your cosine components, right? So these 2 right here. Isn't this force A cosine alpha, and this is force B cosine beta? And it says to subtract those. Right? Why would you subtract them? Oh, well, if you got right minus left, guys, what ideally should this last box be? Is that 0, right? because this is just subtract each other out, right? Hey, do you guys think it's the same story vertically? Like this component up and this component up. If you add those together and then subtract this component down, or actually that would be a full weight down, wouldn't it? Full tension. That up, that down. What should that balance out to? Also 0, ideally, right? You guys gonna see how close, right? Maybe it's not, exactly, but ideally it would be, right? So you guys get to see that too, right? So you guys go with that? All right. So I will be, maybe I'll leave this up as a model. I'll be walking around and helping you guys out, right? And then just turn this lab into the gray tray by the end of class.